to a course on calculus. In the previous lecture, we have seen what is the limit, right? We have not seen the mathematical definition of a limit. We have seen some illustrations and how limits arose, right? Now, in this lecture, we will see what exactly limit is by mathematical, right? Here you may find the definition of limit in a general metric space. Before getting into it, let us define limits in a real line and we will extend it to something in general metric space, right? So, definition of a limit. Okay, we are given with some function on real line. Okay, whenever we are talking about a real line, it means we are talking with the metric absolute of x minus y. Okay, so for every epsilon bigger than 0, there exists some delta positive such that absolute of f of x minus L less than epsilon whenever 0 less than absolute of x minus c less than delta. Here, what is these things? We will see this is the definition of a limit for what the case? Limit x approaches c f of x equals L. Okay, we will say limit x approaches c f of x is L if these things happens. Okay, and I think we have seen some examples in the previous lecture itself. Now let us do some more examples. Let me take f of x to be x square plus 2x plus 1 and let us find limit x approaches 1 f of x. Here you see, do we have any black hole scenario in this case? That is divide by 0 or approaching infinity kind of things. We don't have any such things. In these cases, you may simply substitute it and this is going to be our limit. Okay, and let us take x plus 2 upon x minus 2 and let us find the limit x approaches minus 2 f of x. Okay, here when is the black hole scenario happening? That is when does your denominator become 0 or it grows infinitely? When your x is 2 it happens, but you are looking for the limit at minus 2. So you may directly substitute it. So it is going to be 0 upon minus 4, it is 0. Okay, even some example, we have seen this example already, that is x square minus 16 upon x minus 4. Okay, there we have seen such things when we find limit x approaches 4 of f of x and it happens to be 0.0 and such things happens, and that way we found the limit. Here one more way to find is that we may split this as a plus b into a minus b. So x plus 4 upon x minus 4 upon x minus 4, x minus 4, x minus 4 cancel and you have limit x approaches 4 and it is going to be what? Simply 8. This is what we got already, right? And let us take one more example, 1 upon x. Okay, and limit x approaches 0, f of x is going to be what? It grows infinitely. This is going to be infinity, right? Here we are talking about x approaches 0. Whether you approach from the left or you approach from the right, you are going to get infinity in both the cases. Okay, so it is infinity. And okay, fine. Here what we are saying is that what is the physical meaning of this? whenever you plot these things in a graph, okay, you are talking about x approaches C. Okay, when your x approaches C, suppose let this be your point C. Okay, then what happens to the function? That is what we are finding, right? So according to the C, there must be some value in the function. We don't know what that value is. Here you are choosing x minus C less than delta, which means there is some error region that you fix for your x coordinate in the x axis, right? If you look, okay, here you have fixed some error estimate. Similarly, you have some error estimate in the function as well. Okay, you have something of this sort. Whenever you choose any random points in these things, that is, if you zoom into this, okay, if you look at these things, the function value has to be between these things. This is what the definition means physically. Okay, when you zoom like this, and if it goes away from this, then we say that the limit does not exist. Okay, here what is to be fixed first? You will have to choose your epsilon first. Okay, that is, you will have to choose the error, admissible error for the function. Okay, after choosing the admissible error for the function, you will have to choose the corresponding admissible error for x value. Okay, with the help of epsilon you are choosing this delta, and this delta condition must imply epsilon condition. Okay, we have written in this form. Just don't look at the notations, look at the wordings as well. For every epsilon greater than 0, there exists some delta bigger than 0, such that this happens whenever this happens, which means what? This implies this. First you have chosen epsilon, and based on that epsilon you are choosing some delta. That delta condition must give you the epsilon condition, right? So this is the definition of a limit in a real line. Okay, if we have to extend it to a general metric space in the sense it may be Euclidean space, or it may be discrete metric space, or it may be metric induced by some other metric, or it may be the space may be the space of all continuous functions, space of bounded sequences, it may be anything. Okay, in a general metric space, how do we define limit? Here we are considering two metric spaces, x and y namely. Okay, whenever you choose two different metric spaces, here we don't know whether these two are different metric spaces or the same spaces, the same space with different metrics. We don't know anything about these two things. These are abstract metric spaces, which means there is a metric defined on x. The metric defined on x is denoted as d with suffix x, and the metric defined on y is denoted as d with suffix y. Okay, till now in the previous courses like basic topology, real analysis, basic topological concepts, and sequence and series, we simply made use of D. There we were dealing with only one metric space, and the metric defined on the metric space was assumed to be D. Here we are dealing with two metric spaces, and hence it is necessary for us to tell that this matrix belongs to this space. That is why we are giving this notations. It is just a notation. There is nothing else to do with this. Okay, and we are defining a function from x to y. Okay, are we directly defining a function from x to y? It is not necessary. You may choose some subset of x, and from this also you may define a function. That is, if you are going to consider this way, this may be your e. This e to y you are defining. Okay, you have the possibility of choosing e as the entire x also. Okay, when you say we are defining a function from x to y, then you will not have any surety that it may be defined for any subset. But when you say it is defined for some subset, you may choose your entire set as a subset as well, right? So this is how we are defining a function, and in this E has a limit point P. Okay, I don't know how many limit points does this E has, but among those limit points I am choosing a single point P, and it may be any arbitrary choice. Okay, we have identified some limit point of E. Then we say when x approaches P, f of x approaches some q. Here we will have to see the things clearly, right? Here, where does this x belong? X belongs to E. Okay, and we are saying x approaches P, which means this P, we have told that this P is a limit point of E. Therefore, it belongs to the E closure. We do not have any surety that this P is a member of E. But this is a subset of X and this is also a subset of X. Right? So what we have done is that we have chosen 2 points in X such that when X approaches P. Okay, this X is a variable here and P is a particular point. When X approaches P, f of X approach Q. Where does this f of X belong to? This f of X is a member of Y. Since f is going to be f is a variable which can take any value in X, it means f of X can take any value in Y. Okay, and this approaches Q, that is what we are saying, which means for this Q is also a member of Y. This may be put in a way that limit x approaches P, f of X is Q. Okay, the same thing here. What we have, limit x approaches C, f of X is L. For this we have these things. Whenever this holds, we must have this thing, right? And this is the metric here. What is the case? Here the function is defined from R to R. Here we are talking about the absolute function defined on the domain, and this is the absolute function defined on the codomain, right? It may be also written in this way. These are some random points in the space. Okay, here extend this idea. What do you have here? Here this will be replaced by general metric D with suffix x of x comma what? Here see, there we have P. So this has to be less than delta. That is what. So when you have this will give you, come here. This may be written as d of f of x comma L, right? So is less than epsilon. Here L is replaced by Q. Okay. So this will imply this. And here also we are, first of all, we are choosing for every epsilon bigger than 0, there exists some delta positive such that these things happening. Okay, the function has a variable x and that x can take any value in E. That is what we are mentioning here. That is the additional thing that we have done here, right? Okay, we have told here in this definition, we have told this P is a limit point of E. Is it necessary that the P is not a member of E? Sometimes it may be a member of E as well, right? And in those cases, do we have any assurance of telling limit x approaches P, f of x is same as that of f of P? No, it depends, right? So whenever you have your P is a member of E, we cannot blindly say this happens. Whenever P is not a member of E also, we cannot blindly say this happens, right? So this will be true only if the function is continuous. The notion of continuity we will see in the upcoming lectures, right? As of now, this may not be true in general. That is what we have to remember. We have just seen the definition of a limit. Now, let us explore a theorem which relates limits with the sequences, right? Here, you may see in the theorem statement that we are taking two metric spaces, okay? X and Y are metric spaces here, and we are taking a subset of X and F maps E into Y, which means the scenario that we are talking here is this scenario, and P is the limit point of E, these things. Those things we have seen in the definition of a limit, that is what we have considered, and here we have this, which means what? When X approaches P, F of X approaches Q. This is what we have. Okay. This will happen if and only if this happens. What is given here? In the place of P, we have some Pn, and limit as X approaches P is replaced by N approaches infinity. What is this Pn? This is some sequence in E such that it converges to P. Okay, it converges to P, may be written in these two forms, and here this thing is the important one which we have to note. No element of the sequence is same as that of the limit of the sequence. That is what they have given, right? So with this informations we will prove the theorem. Okay, first let us assume that limit X approaches P, F of X is Q. If we assume this one, then by the definition, what are we going to get? For every epsilon greater than 0, there is a delta positive such that d of dx comma p less than delta implies d of f of x comma q less than epsilon. This is the definition of the limit. Here we will have to specify which metric we are talking about. For this we are talking about the matrix that is defined on X, and for this we are talking about the matrix that is defined on Y. This is by the definition of a limit. Okay, so by our assumption we get this, and we will have to prove this one. Okay, in order to prove this, what is the thing we have to take? We have to take some sequence which converges to P. Okay, suppose Pn converges to P and Pn is not same as P. If we take this way, then we will have to prove this happens. This is what they have given. Okay, now by the definition of convergence, what are we going to get? By the definition of convergence, for every epsilon positive, that the epsilon means what? Some negligible quantity. There is no necessary that we will have to represent that by epsilon. Okay, that may be chosen as any positive quantity, very negligible quantity. Even here we are talking about two positive quantities, epsilon and delta. These two are also some negligible quantities. Hence I am going to choose my epsilon to be the delta to be the epsilon value here, which means by the definition of convergence, for every delta positive there is a positive integer n such that d of Pn comma p less than delta for n bigger than or equals n. What is the metric that we must specify here? We have taken the sequence, okay, in E, which means we have to specify the metric on X. So this is going to happen. Okay. Now you will have to compare this with this. Okay. What is happening? After this stage, the entries in the sequence satisfy this condition, which means this is same as that of this. Even here you may notice that what? Pn is no element of the sequence is not same as that of P, which means here also you have this condition. So this is going to imply whenever this happens, this will happen, right? So this implies your dy of f of Pn comma P less than delta. Sorry, Q, right? We have Q. And this is true for n bigger than or equals n. When this is true, we may say what? We may say this happens if and only if Pn converges to P. Or it may be written as limit n approaches infinity, Pn equals P. So this will give you what? Hence, limit n approaches infinity, f of Pn is Q, or you may say f of Pn converges to Q. Okay, this statement is not specified in the theorem, but actually what we mean is this. Okay, we have done the first part of this theorem and we will do the converse part. Conversely, what we are going to assume is that there is some sequence Pn in E such that no Pn is same as that of P, and limit n approaches infinity, Pn is P. Okay, for which what is happening? And limit n approaches infinity, f of Pn is Q. This is the assumption that we make, and with this we will have to prove this happens. Okay, suppose limit x approaches P, f of x not equals Q. We are doing by contrapositive approach. Okay, in this case we can identify some epsilon bigger than 0 and for any positive value delta we have 0 less than dx of x comma p less than delta, but dy of f of x comma q is bigger than or equals epsilon. This will happen. Okay, here in the definition also what we are saying is that when this implies this, okay, so this has to be there for always. Okay, this, if this happens, this implies this. Suppose this is happening, then we say that limit x approaches P, f of x is Q. Okay, when that is not going to be the case, this will be there, this will be violated. Okay, here actually if we try to rephrase this, for any delta we have some x in E such that this is happening. Okay, so whatever may be the value of delta you choose, epsilon is some fixed quantity, and for which whatever may be the delta value you choose, this is going to happen. Okay, for delta, let us choose delta to be 1 upon n. So when n is 1, you get some x in E, right? So when n is 1, we identify P1 in E. So let us say this to be equation 1, okay, such that 1 holds. Similarly, when delta is 1 upon n, we can take Pn in E such that 1 holds. Okay, here you are identifying something, right? And we have assumed that this Pn converges to P, all those things are there, right? After identifying this, can we come to a conclusion? Yes, this will lead us to the conclusion. We will have to see what that is. Okay, just have a close look at it. What are you going to get here? Now, these things are happening for what? For this case. Okay, we know that Pn converges to P. Right? So, using that idea, when n approaches infinity, Pn approaches P, and that is there, but dy of f of Pn comma Q is bigger than or equals epsilon, and this implies what? Just because of this implies what? Limit n approaches infinity, f of Pn is not Q. This is what we are having, but this is a contradiction to our assumption. But this is a contradiction. Therefore, what should we have? Hence, limit x approaches P, f of x is Q, and this completes the proof of this theorem. Okay, here let us see a corollary kind of a thing. Okay, if the limit exists, okay, suppose limit x approaches P, f of x is Q, this Q is unique. Suppose if we have to prove it formally, then we may make use of this theorem as well as the limit of the convergent sequences are unique. Okay, combining those two things here, if it has to be true, then we must be able to identify some convergent sequence such that these things are happening. The limit of the convergent sequences are unique. Therefore, it gets back to this. Okay, so in this theorem, what we have proved is that whenever we are saying that the limit exists of a function at a particular point, we can identify some sequence such that it converges to the point, and these things are happening, right? And also the limit of a function at a particular point is unique. Okay, thank you for watching.